12. No, that didn't work. Did it work? Oh, it did work. Okay. Okay, so hi to all of you on YouTube, because you missed a class for some reason. Alright, so, okay, binomial coefficient is all combination. It's the number of ways to choose k object other than total. And the formula is here. We went over this in the first class, I think, and you remember this, right?
Yeah.
Yeah. You won't go over it too much, just, you know. Alright, so we actually haven't talked about block walking yet, so I guess we can talk about that. Alright, I guess we'll just start with an example. We'll give you some time to think about it. You can just shout it out if you know how to do it, or type in chat. That's also fine.
Okay. So the first one is just like 11 choose 4.
Yeah. So if we have a grid, which I don't, so how'd you get 11 choose 4? I'll just
So basically he has to take 11 steps, and
Yeah.
4 of them have to be up, so he has to choose the spots to be up. There's 4 of the.
So basically we can arrange this randomly,
Yeah.
rearrange it, and then for every rearrangement is a path.
Yeah.
Yeah. So, okay, so you already know the concepts, so I guess, yeah. Number 2.
And then it's just like that, subtracting 5 choose 2 times, I think it's 4 choose 2? I mean 6 choose 2.
Let's see. Yeah, 5 and 6. So, yeah, this is complementary counting. You just pick the number of ways to go to, subtract the number of ways that you can go, that you pass through the point 3, 2 from the total. And, yeah, so I'll just write it in here just for keeping. This number of ways to arrange that, and then for this one, I'll do it here. It's 11 choose 4 minus 5 choose 2, and I think 6 choose 2, which is some number. I don't think we have to evaluate it.
Yeah.
Alright, number 3, I guess, do you know how to do this question?
Okay, so if you go to B first, there's only one way.
Yeah.
If you go to E, then you have... Well, if you go to D, you also have one way. But if you go to F, then you have 2 ways. So it's 4, I think.
Yeah. So, yeah, you're sort of like using kind of logic to figure this out. I think like a better way, honestly, would be just for each point. It's very similar to what you did, but like for every point, just write down the number of ways you can go there.
Yeah, I've seen that before.
Yeah. So, yeah, your logic is probably simpler, but it can get confusing maybe. But whatever works, I guess. Hey, someone's here. All right. Looks like we have our second person here today. So far we just went over combinations in this thing. So you can use the chat too if you want. So I'll just go over the first question. Like, if you want to go from 0, 0 to 7, 4, you have to go up 4 times and to the right 7 times. So you have to rearrange this sequence, the UUUR sequence. And for every rearrangement, there is a valid path to 7, 4. And the number of ways to do this is basically pick 4 letter U's out of the 11 letters. So that's just 11 choose 4 by the definition of combination or binomials. Yeah, and number 2 is complementary counting. You subtract the number of ways to go through 3, 2. And if the grid is like arbitrary like this, even if it's on a grid, sometimes the grid is still like arbitrary. There are arbitrary cuts. Then just for each next to each number, you can just write the number of ways to go there. And for like a vertex like G, it's a number of ways to go from from B to the number plus the number of ways to go from F. So if this is 1, this is 2, it's going to go and become 3.
Wait, isn't F just 1 though?
Is it? Oh, it's 1. So ignore that, I guess. Yeah, my bad. Alright, I'm deleting everything. So yeah, the F is 1 because you can only go from E to F. And then you add these up to get 2, add these up to get 2, and add these up to get 4. And yeah, if you want to split it up somehow, like let's say B is 1, because obviously, and then if you're at E, maybe you can do like, this is like a grid now. So maybe you could do like 3, choose 1, so 4. But just writing it out is probably the best way. Any questions?
No, not really.
So, okay, here's Pascal's triangle. So, I mean, we start at 1 at the top, and then there's like invisible zeros, and each number is the sum of the two above it. And I guess we'll explain more on the next slide. So you get this triangle sort of thing, and it becomes important with combinations. These are identities. Hold on. The Google Calendar doesn't have this class on it. What? It does. I thought. It does for me. I don't know. That would explain why no one's here. Let me like go to an incognito window and like figure it out. I guess for now you guys can look at the identities and see if, I don't know, you can prove any of these or something. Okay, for now. So there's like a lot of ways to prove identities, and there's like 3 main ways. I think this is on a later slide, but you can use like a block walking argument. You can also use a committee forming argument, or you can just use algebra. For now, I'll try to find the calendar. It's not on there. That's really weird. Because it's on there for me. I mean, for my account. It's like there. Is it hidden? Let's see.
I had it on my like personal Google Calendar. Like I joined the Google Classroom and just put it there for me.
I don't know what's wrong. Can I do save? Alright. It isn't on the Google Calendar. It's weird. Wow. I mean, it's showing up on my thing. You guys can see it in the video. Not in the class right now. Can I email guests low key? I'll do that. Wait, I can't email to everyone. Darn. I guess I'll go to my Gmail and try to do something about that. Unless this is the wrong person's email. Should I? No, this is the right one. Alright, I guess. I don't know, next slide. Identities continue. Yeah, so algebraic, block walking, committee forming. Do we prove these? No, we don't. Okay. So these are some identities that we should know. I'm trying to multitask while doing this. I still have no idea how to set. Where are all the people in math counts? If you guys can like stay longer than like until 6, we can extend the class a bit because things.
My schedule's open, so.
All right, cool. Let's see. To me, that's not how it works. Do you know if there's like a list of all the people taking math counts and stuff?
Shouldn't they be in Google Classroom?
Is there? Okay, let me go to Classroom then. People. Can I email all or something? Select all and then email. Yes, I found it. Um, right account. Like all the email that I have. Okay. To myself. What? Okay. Ugh. Okay. And I am sending. Alright. I guess we can just like prove any of these. Did anyone like try to prove any of these or to like have any ideas, whatever, stuff like that?
I do for the first three.
Alright, that's nice. Um, I mean, do you want to explain it or should I explain it? It's up to you.
Either way is fine. I mean,
Alright. Do you want to explain any of them? It's fine if you don't want to. If so,
I
if you
mean,
do.
sure.
Alright.
So like the first one, it's like so n choose k. Like if you have a committee of n people and
Yeah.
you want to choose k of them, it's the same as like not choosing n minus k.
Yeah. So out of n people, you can choose. There we go. There's the people coming in. Um, did I click admit? Did I click deny? Uh, whatever. Yeah, I don't know why it's not showing up on the thing. I don't know. Did the person disappear? Okay, so you can either if there's n people, you can and you want to pick k of them for a committee. You could also pick the n minus k people to not be on the committee. So yeah, n choose k's, n choose n minus k. Alternatively, block walking argument's pretty similar. So basically, committee forming is something like this. You have to form a committee, and you form it in two different ways. And the binomials that you get from those methods are equal, obviously, because there's an equal number of ways to make the committee. Actually, I'm not sure that person went. Did I entry? Whatever. So, if you want to do block walking, this is Pascal's triangle, and there we go. All right, nice. I'll finish what I was doing before going back and trying to fill in people. I guess. I mean, I guess when everyone else arrives. Okay, so the block walking argument is, let's go back to Pascal's triangle. I guess I should probably explain everything about Pascal's triangle because I didn't. So, if you look, this is the 0th row. This is the first row, second row. And let's say you pick this random thing here. This is 5 choose 2. And it's in the 5th row. So this is row 5. And it's the second diagonal. So this is the 0, first, and second diagonal. And there are multiple ways to prove that the Pascal's triangle forms binomials. This, I guess, is another way to prove things, I guess. One way is because, consider this thing here. So we just did block walk on the previous side, and we said rearranging the up, up, right, right, right thing gets you the number of ways to walk from 0, 0 to 7, 4. So if you want to walk from 0, 0 to, I think this is 3, 2, then there's 5 choose 2 ways to do that. And yeah, another way to prove this is, let's say this is 6 choose, what is this, 6 choose 4, and this is 6 choose 5. We can actually use one of the identities in the next page. I guess we're going to prove that in using this, but whatever. And the sum of these is the next one, so that's the thing. That's the that's like an inductive proof that Pascal's triangle has binomials. And yeah, any questions about that?
Wait, so is block walking literally like just like paths on a grid, but like different?
Yeah. So this is like a big grid. So if you look at the blue, I guess I'll make it red. This red thing here, you can think of it like if you tilt your head a bit, it looks like a 3x2 grid, or I guess it's you have to go this way 3 times. What happened? Oops. Hold on. All right. You have to go this way 3 times, and you have to go this way twice in order to get to this point. So, and if you look at each way to go, then each path is counted exactly once because yeah, this is probably the important part. If you look at this this number here, it's this plus this. So if you want to get to the 10, you either have to come from the left or from the right. I'm not sure why I didn't say that. Yeah, sorry. So if there's 4 ways to go here and there's 6 ways to go here, then there's 10 ways to go here. That's like this thing we did here. So that's just this thing kind of. We added together the 2 previous ones. And we could do the first 2 questions like that too. Like if we have like a big grid, we could like write out 1, 1, 1, 1, and it'll actually look like Pascal's triangle, but like tilted a bit. Also looks like everyone left, which is interesting. All right. Anyway. Okay, so does that answer your question?
I kind of get it now.
Yeah. Yeah. So you could better write Pascal's triangle as like, hold on. Ooh, my pen is like weird. I'm just gonna do it with my hand. So it's like one. This top one is 0, choose 0, because that's the number of ways. So Pascal's triangle, each thing is the number of ways to go from the top vertex to that vertex while only going down. So this is 1, choose 0, 1, choose 1, 2, choose 0, 2, choose 1, 2, choose 2. And if you evaluate all these, it should become the Pascal's triangle. And actually, a lot of these identities might be a little like hard for math counts. So, I mean, we won't go over most of them. I mean, we'll go over them, but like not in detail. But I guess it is important to realize that Pascal's triangle is like that. There's this bijection between committee forming and like going to like pathfinding. And that the reason why there is a bijection is because committee forming is like the definition of the binomial, and then if you do pathfinding, you can cleverly say like in this example, you have to go like either left, 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 right, right, which would be this path here, left, 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 and then right, right, or any rearrangement. And since by the thing to the right that says 4, 6, and 10, you have to just add up the previous 2 to get the next one, and so that's how binomials work. Questions? Okay.
No, I think I'm good.
All right. Hopefully, I guess these identities will probably be cleared up, maybe. So yeah, I assume you did all of these with like a committee forming argument because hadn't actually explained the block walking yet.
Yeah.
Yeah. All right, Michael's back. So yeah, I guess we'll do these with the committee, all the arguments really. So committee forming is you have to choose k people to be on the committee, but you can instead choose the n minus k people that are not in the committee, and it's the same thing for both. So you get this identity. And if you have a block walking argument, so remember that each square, the number in that square, let's say 36, is the number of ways to go from the top vertex to that vertex, not vertex, but like that thing in the triangle, while only going down. So if you want to prove that n choose k is n choose n minus k, so that would be like a reflection. So this would be like, if you go back to Pascal's triangle, it would be, oh, that's not Pascal's triangle. 36, I think, is like here somewhere. Anyway, let's do the 35. The 35 and 35 are like opposite each other, and basically the claim is that Pascal's triangle is like, you can reflect it and it's the same. And that's pretty clearly true because Pascal's triangle is symmetric. There's no reason to be asymmetric because we start off with a single 1 and the rule is symmetric. The number of ways to go from here to here, I guess you can also just use the bijection into a committee forming argument, kind of. So you can just say, like, the number of ways to rearrange left, 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 right, right is equals the number of ways to rearrange right, 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 left, left. And, okay, does that make sense?
Yeah.
Cool. So the third way of proving identities is algebraic, and this is usually the most boring. Just annoying, I guess. So, like, if you ever get like a proof question, these are obviously too simple for like actual Olympiads, and obviously like MATHCOUNTS doesn't have proofs. But like, if you get like a question to prove this in some case, algebra is sometimes good. Like in the first case, it's actually pretty simple, but in a lot of these later ones, it's actually like really hard to do. Anyway, the algebraic proof of this is if you just do the formula for both combinations, you get, this, which is obviously true because you can just switch them around. Alright, so any questions about the first identity? And if not, we can go on to the second identity. Alright, so the second identity states that, let's go back. Hold on. Is it lagging? It's lagging on my computer screen. Okay. So it's proving that the sum of n choose 0 plus n choose 1 plus dot dot plus n choose n equals 2 to the n. And if you look at these terms in the Pascal's triangle, let's say n equals 6, they're actually these numbers. So it's saying if we add all these numbers up, the sum equals 64, which is 2 to the power of 6. Anyone have any ideas how to prove that?
Yeah.
Go ahead, if you feel like.
So, like, this is essentially the number of ways to choose a committee of any size.
Yeah.
For n people, so everyone can either be in the committee or out of it. So it's just 2 to the n.
Yep. So yeah, exactly. If you do the committee forming argument, this is the number of ways to form a committee with 0 people, 1 person, 2 person, 2 people, all the way up to n people. So just any size. And then for each member in the committee, you can either pick it or you can not pick it. Pick that person, not it. So 2 to the n because there's 2 ways to choose each person. A block walking argument is very similar. You just pick right or left at each step randomly, and it's 2 times 2 times 2 times 2. Alright, so I guess if we didn't go over binomial theorem in the previous class, in the algebra class, I guess we'll go over it now. So binomial theorem states that, I don't have really much room to write it here. Maybe I have it in the next page. I do. That's an eraser. X plus y, that's not a plus, equals x to the n. I guess I'll write it out fully. N choose 0, x to the n, y to the 0, which is just x to the n, but with a bunch of other terms, plus n choose 1, x to the n minus 1, y to the 1, plus n choose 2, x to the n minus 2, y squared, plus dot 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 plus and choose n, x to the 0, y to the n, which is, again, simply just y to the power of n. If you want to prove this, let's just write out this explicitly. So it's x plus y, x plus y, x plus y, dot dot dot. Let's just do 3, n equals 3. So in this case, let's say we want to find the x squared y coefficient. Let me write the 2 smaller. That's a z. Okay. So if we want to find the x squared y coefficient, we have to pick 2 x's and 2 y's out of these 3. And because of the definition of combinations, there are 3 choose 1 ways to do that. So we can pick like x here, y here, and x here. So, yeah, that's binomial theorem. Of course, a new formula will always take time to get used to, but does this make sense at least?
A little bit.
Okay, yeah, this is brief, I guess, but I guess I'll do n equals 3. If you do x plus y cubed, it's x cubed plus 3x squared y plus 3xy squared plus y cubed. And if you look at the coefficients, which are 1, 3, 3, 1, that's just the coefficients of the Pascal's triangle. That's the third row of Pascal's triangle, which is 1, 3, 3, 1. And that's just how the coefficients of the expansion works. Yeah.
Wait, so is it like, let's just say there's like 2 y's. Is it like n choose 2? Because out of all the x plus y's, you have to choose 2 of them to have a y and not an x.
Yeah. So
okay.
there's n total, and then if you want like k y's, then there's n choose k ways to choose the y's. So that's the proof of binomial theorem, because and then just expand it out and then like write it out in this form, and then choose the number of. You can either pick the left term or the right term for each spot, for each factor. So there's n choose k ways to choose y to the k and then x to the remainder. I meant x to the n minus k, y to the k. So if we go back, if you want to prove this algebraically, let's go to the right again. Let's say we put x equals y equals 1 in here. What happens? Anyone?
You just lagged really bad.
Okay, yeah. If you put x equals y equals 1 into the binomial theorem, then what happens?
You just get 2 to the end?
Yeah. Yeah, there's a chat. That's the first chat of the whole class. Oh, it's not. Never mind. What am I doing? There's a lot. Anyway, it's 2 to the n on the left side, and then on the right side, we get n choose 0 plus n choose 1, and so on. And that's just binomial theorem. I mean, not binomial.
Oh, that's really nice.
Yeah, that's the identity we want to prove. So, yeah. So that's how binomial theorem ties in here. Another like interesting thing about this thing is, let's say you put x equals 10 and y equals 1, then you just get the powers of 11. So if you look at Pascal's triangle, let's go back. You may notice that these are like the powers of 10. I mean, powers of 11 until the 10 term appears. So 11, and then 11 squared, 11 cubed, 11 to the 4th. It's lagging, the screen's lagging. So yeah, those 4 things are powers of 11, and the proof of that is just binomial theorem. Let x equals 10 and y equals 1. Okay, any questions? Yeah, it is the proof of it. Alright, I guess we'll go to the third identity. So this is like a short thing that can also be proven algebraically, but I don't want to do that because algebraic proofs take a long time, and they're not really the point. But we are actually already went over this. If anyone wants to say the answer, let's go ahead. Yeah.
Is it like if you have n plus one people and you want to
Yeah.
choose k plus one of them, you like let like one of the people be like special kind of, and then there's like two possibilities. So either the special person is in or they're not in. So if they're in the group, you have n people left, and you only have to choose k. But if they're not in the group, you have n people left, but you have to still have to choose k plus one.
Yeah. So that's the community for argument. Um, if you want to do n plus one, choose k plus one. That's the number of ways to pick k plus one people out of n plus one. And yeah, you take one outside, a different person, a new person, I guess, and you can either put them in the group or outside the group. If you put them in the group, um, there's n choose k ways to choose the remaining k people here, and then if you don't put them in the group, you have to choose k plus one of them. So that's the proof. If you do a block walking argument, we actually already talked about this. Remember when we said this thing here to the right? We said 4 plus 6 equals 10, and if you actually write that out in a binomial form, that's actually just the identity where you add the two things and you get the next one. So yeah, and then an algebraic proof also exists. So basically, there's like 3 proof methods for all of these. These aren't the most important, so I guess we'll go a bit quicker on the last one. By the way, does anyone know the name of the last entity? Yeah, hockey stick identity. I don't know where Pascal's triangle is. I guess it's on the next page? It's not on the next page. Is it on here? It is not. I guess we're like running out of space. So does anyone know how to prove this? Of course, this is like a higher level identity. It's like late math counts at least.
Can we use like a similar idea as the last one, but it's like more complicated?
Yeah, we could.
It's like the last term on the left hand side. It's like you denote one special person that has to be in, and then the first term of the left side, I guess. No, that doesn't make sense. Hold on.
All right. Yes. Yeah. I'll give you a bit of time to think about it. And if any of you other two want to say anything or put it in the chat, let's go ahead. See if the calendar's updated yet. I can't check. I guess I'll have to go to here. Yeah, I don't know what's up with the calendar. That's weird. That's really weird. Can I duplicate it? And then save it. Nope. What if I duplicate the Olympiad class one? Oh, I didn't save it. Alright, anyone have any ideas? It's a harder identity, but All right. I'll just see if this works. 5 p.m. to, let's say, 6. I'll write 6:30, even though it probably won't go that far. Google Meets is not that, so I don't know how to. All right, I guess I'll just have the same link and go in there too. Oops. All right, whatever. So let's go to the hockey stick identity and try to prove it. I don't know if you have any space to prove it. Ooh, I can do that. Whoa. Let's see. I guess I'll prove it here. Okay, so let's line up n people. I guess it was n plus k people. I forgot the identity already.
It's n plus 1. Choose k plus 1.
Oh yeah, n plus 1 people. All right. So let's line up n plus 1 people. And we can have some of them in the group. We want to choose k plus 1, I think. K plus 1 people. Yeah, k plus 1 people to be in the group. So we just consider the leftmost person who is in the group, in the committee or the group. And okay, I'm joining the other class just in case. Okay, so if we look at the leftmost person in the group, let's say it's this person, right? So the first person is not in the group and the second person is. How many ways can we choose people in the last groups so that we have a total of k plus 1 people? So we know like the second person is the first in the committee. I don't know. I have no idea. Whatever. So okay. Any ideas? Okay. So we have a remainder of n minus 1 people, right? We have n minus 1 people remaining who could be in the group because we know the first person is not and the second person is. So that's n minus 1, choose k, because we need k more people in the group. So if the first person is the first person in the group, so let's say this person to the left is in the group, then it's n choose k, because we have one more person that could be in the group. And then if you keep doing this until something, just if you keep doing this, we end up until k choose k, because the last k people have to be in the group. Does this make at least a little bit of sense? It's not a very important identity to know for math counts, but
it makes
yeah.
Yeah.
Let me try to go for a path walking. Actually, I'll go back to this. Hold on. This. So if we have Pascal's triangle, what we're trying to prove basically, let's say this is a side of Pascal's triangle. We want to prove that this plus this plus this plus this plus this equals this. Ooh. So this is the hockey stick identity because it looks like a hockey stick, kind of. It's like it just turns. And a way to prove this is that let's add an invisible 0 here, right? Because everything not in the Pascal's triangle is just a 0. And now let's combine them one at a time. So we combine this one and this one. Let me do it in red. So we combine this one and this one. We add them up and we get this. And then we add these up and get that. Add these up and get that. Add these up and get that. And then add these up and get that. So we added an invisible 0 to the sum. And then by just going down and adding them up recursively, we get the value we want, which is there. Does this make sense? Kind of.
Yeah.
Yeah. I guess the last one we can go over very briefly because that's the one on the screen here. If you didn't really understand that, you'll probably see it later. It's not very important, so I'll go over that. Hopefully, that's okay. All right, I guess I'll give you like a bit of time to think about this one. Hat identity. I don't know if that's the name for this. I didn't. I don't know about that. Maybe it is. I'm not sure. Yeah, so this one's I think maybe harder to prove than the last one, maybe. Or any ideas? Okay. Yeah, I don't really expect you to get this one. So, 2n choose n is this number here in Pascal's triangle. Is that clear? And let's say we want to walk to this path. So we're using a block walking argument. So we have to stay within this parallelogram. And if you look here, that means we have to intersect this row once somewhere. And let's say we intersected at this red point here, this point. So let's say we want to get to 2n, choose n, and we go in the middle, 2n, choose k. Now, what's the number of ways to go from here down to here?
N plus. Wait. Two n minus k, choose.
Yeah, it may be a bit hard to visualize since Pascal's triangle is like a triangle and not like a rectangle. So we can honestly do this with a square. The number of ways here is 2n, choose n, and we have to go through this diagonal. And let's say this is n, choose k. So n, choose k. What's the number of ways to go from here to here? So we go from to here and then to here.
Oh, n plus k, choose k.
N
Time.
plus what?
N plus k, the first part is n plus k, choose k.
No, it's just n, choose k. We're taking n total steps, right? That's why we land in the diagonal.
Yeah.
Yeah.
N choose k times. And we have to do 2n minus n is just n.
Yeah.
Then n minus k is just n minus k.
Yeah. So, if you're not confused how we got that, then we have to take 2n total steps, right? We have to take 2n total steps, and we already took n of them. So we have n left. So that's where we got the n from. And if you look at the bottom of the binomial, there's n. We have to take n steps to the right, and we already took k steps to the right. So we have to take n minus k steps more. And if you notice, we already know that n choose n minus k is n choose k. So then that's where we get this n choose k squared term in here from, in the identity. And if you add this up over all of the possible places you can go, then you get this identity. Alright, any questions? Alright, cool. Yeah, so this is another example. I don't know if I should do this. This might actually be familiar to you guys. I guess we can do it because if you like, a lot of people So this showed up on the Amy actually, and so this is of course like a hard example, but I think it does help because a lot of people when doing this just like bashed it out, and that I mean I don't really know of many people that succeeded while bashing it out. Like a lot of them just failed. So it's good to think about this in a clever way. All right, let me just write it out so it's a little easier. 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's say we pick 4 men and 5 women. I'll circle those better. Alright, I'll let you guys think about this for a bit. Yeah. Okay. Alright, any ideas? I know this is a hard example. Okay, so we can pick the number of men and the number of women, but how about we pick the men and then the women that are not on here? So let's pick just these two. So, yeah, we're picking this and this. That's the committee. So this is a new committee. It's the men that were on the first committee and also the women that were not on the first committee. How many total people are we picking? 11. Yeah. Is it always 11 or is it different?
Wait, so
Yeah, always.
yeah, it's always 11.
Yeah. Because there's exactly one more woman than man. If we do the algebra or anything, we get exactly 11 people on the new committee. So that means the total number of people, the total number of ways to make committees is 23, which is 11, and that's just the answer. Because if we have the second committee, we can also go back to the first one. I mean, this may seem unintuitive to you. Actually, I think on the contest, I wrote out the binomial sum, so it's 11 choose 0, 12 choose 1, plus 11 choose 1, 12 choose 2. And a key thing about a lot of these questions is just switching the indexes. So the 12 choose 1, instead of 12 choose 1, we write 12 choose 11. Instead of 12 choose 2, we write 12 choose 10. And if we do this, then if you see, we end up with this identity, Vandermonde. This is way too advanced. I won't actually go over this, but this is an identity that exists. And honestly, the question was just do you know this identity? But we can figure it out with a committee forming argument if we don't know it anyway. All right. Any questions? It's not the most important topic for math counts. So. All right. Yep.
Wait, can you go over why it's 23 choose 11 again?
So we always choose 11 people, right?
Yeah.
So let's say the 11 people have let's say 6 men and then 5 women. Instead of choosing this committee, which doesn't satisfy the conditions, we choose a second committee, which has the same number of men, the same exact men here, but also the women that are not on the committee. So the ones that are not on the committee. So that's 12 minus 5 equals 7 women. And this always satisfies the condition that there's one more woman than a man. If you do the algebra, kind of. So that means there's like a bijection. The number of ways to pick a committee of 11 people is the same as the number of ways to choose a committee of one more woman than a man or whatever. It's like, I don't know what argument you chose before. It's like, yeah, it's just like you choose the people that are not on the committee, but only for the women. Or you could do only for the man, it's fine. You get 23, choose 12, which is the same thing. Anyway, does this make sense?
Kind of.
Yeah. I mean, this is obviously a hard example, so it's fine if you don't get it. Anyway, we're almost getting like to the normal ending point. Also, no one actually arrived for some reason. Also, did the thing show up in the calendar? It did. What? I don't know what's going on. I don't know. Oh, it's because not in Summer Academy, maybe? That could be a reason. Let me see. It showed up. What? Okay, that's kind of dumb. Darn. Alright, I figured it out. It should show up now. Yeah. Dang, that's really weird. Oh well. Alright. I'm scrolled up. Yeah, it's there now. Alright, so I guess we'll go to the other... So there was homework also, but I assume you don't want to go over that yet. The things are all online, by the way. Alright, so hopefully we'll go into some easier topics. I mean, they're not like easy, but like easier than the previous ones. So I guess we'll start with this. Expected value is the average value of something, a random variable. So if there's a probability of P to get A, and then a probability of Q to get B. So like if there's a 1/4 chance of 1, 1/4 chance of 2, and a half chance of 3, then you get like 1/4 plus 2/4 plus 3/2 is the expected value, which is like 5/4. Does anyone know the answer to the question? I guess I should say a fair 6-sided die.
Shouldn't it just be 3.5 because that's the average of all of them, and they're
Yeah.
all equally likely?
Yeah, so it's the average of all of them, which is 1 plus 2 plus dot 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 plus 6. I'm too lazy to write that out. Over 6, which is 3.5. And this is a good thing that illustrates that the expected value doesn't have to be a possible value. You can't get exactly 3.5, but the average is 3.5. Alright. So, the biggest thing about expected value is that it is additive. So, the expected value of A plus B is always expected value of A plus the expected value of B. No matter what. So, like, yeah. It does seem kind of unintuitive because, like, sometimes, I mean, if they correspond, let's say A is only true, like, mostly when B is true. Regardless, it's just A plus B. You can add them up separately. Anyway, I guess we can go to the second question. Yeah, I'll give you guys some time to think about that. Oops. 28. I think it's going to be more than 28. Let's see. Oh, okay. I see where we got 28 from. Yeah, but it's you have to consider the pennies that you don't flip over as well, because some of them just stay on the table. Yeah. So I think, yeah, 46 should be the answer. So basically what you did here was you did linearity of expectation, which is the thing where you add the numbers. But you did it for each penny. So let's think about it. For each penny, there's a 40% chance that it's flipped over, and if it's flipped over, then there was a 70% chance that it becomes heads. Right? And if it's not flipped over with a 60% chance, then there was a 30% chance that it's already showing heads. And this turns out to be 46%. Now, you have to remember that if, let's say, the first penny is heads, then the second penny is probably not heads. It's less likely to be heads, I think. Or it's either more or less likely. Let's say, like, the first 70... No, the first 70 coins are all heads. Then the chance that the 71st coin is heads is 0. So these each penny is not independent of the other ones, but we can still add the probability. So we have 46% chance for each coin. We can just multiply that by 100 to get 46. Is that clear? Alright, so you guys can try the second question. I'm not sure where I actually saw this problem. I saw it a long time ago. It may not actually be in like a competition preparation book, but I mean, it's an interesting problem. Wouldn't it equal more boys? What do you mean by that? Like the boys' population goes up? And if so, why? The mayor's argument here is that like some families will have like multiple girls, but no family can have more than one boy. So, you know, that's the mayor's like that means, you know, girls go up. Okay. But let's think about this mathematically. Alright, any ideas? Okay. So, a simple argument is that every birth, let me do it in green. You could do geometric series, yeah, that does work. 2 to 1. Okay, we'll do the geometric series thing later. Every birth, 50-50, right? And let's say there's like 50,000 births. I don't know. That means the expected number of births that are male is 25,000, and the expected number of girls is 25,000. Because they're not independent. Because like, if the last birth was a boy, it can't. Actually, they are independent. Yeah. Anyway, by linearity of expectation, every birth is 50-50. So that means if you have like a bunch of births, the overall is also 50-50. And it seems like counterintuitive, kind of, because the Mayer's argument kind of makes sense, but there's a lot of unintuitive things. Actually, let's go prove this with a geometric series. So, actually, the geometric series thing doesn't take into account when a family like stops having children by choice. But let's just say every family has children until they can't, or something. Then the chance that there are, so that means every family has exactly one boy, because that's when they stop. And the chance of 0 is 1/2. 0 girls. The chance of 1 girl is 1/4. Ooh. 1/4. The chance of 2 is 1/8. And so on. So we can add this geometric series. I'm not sure if you learned this in algebra, but we let this be S, and then I don't have much space. If we do S over 2 equals 0 times that 1/4, 0 times 1/4. So this is an arithmetic geometric series because there's a term that goes up linearly. So that's 3 times 1 over 16, and there's also a term that goes up exponentially. Okay, so this is S over 2. If we subtract these, we get, hold on. Yeah, if we subtract these, we get S over 2 equals 1/4 plus 1/8 plus dot 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 equals 1/2 by the geometric series formula. So S equals 1. So the expected number of girls per family is 1, just like the expected number of boys. Yeah. Any questions? By the way, yeah, I mean, class is technically over, I guess, because I don't. If you have something to do, like dinner or whatever, you're free to leave. But since we kind of spent a lot of time doing random stuff, trying to get people in, I guess we can go a bit over time. All right, I guess we'll go to the 4th question. Okay, so states. Again, this is on the advanced side, but I've definitely seen MATHCOUNTS questions use states. Actually, I remember something from 2018 Nationals, one of the team questions. I think number 9 was states. I remember that because Luke got it wrong and I got it right. Anyway, whatever. So the states of things. So, okay, let's just go into the example, because it really doesn't make sense without the example. Also, no chat for a while. Anyway, so there's 4 rungs. Let's just do them to the right because I feel like it. So there's rung 1, 2, 3, and 4. Hi. Yeah. So he starts. The frog starts here, and he can go up or down 50-50. Coin flip every time. And what's the probability that he reaches the top without falling off? And so the theory of states is that you set a variable for the probability. So this is P1. So the P1 is the probability. That's what we want to find. Let's say the frog is at rung 2. Then the probability is P2. And probability is P3. And if you're already at the top, the probability is 1. And if you're at the bottom, the probability is 0. So We can use a system of equations. So the probability once you're on rung 1, there's a half chance that you fall off, so half times 0, plus a half chance that you go 1 up, so P2. So basically we get P2 equals 2P1. If we do the same for the other things, let me do it up here. P2 equals P1 over 2 plus P3 over 2. And similarly, P3 equals 1 half plus P2 over 2. And so that's just 3 equations, 3 variables, so we can solve it. I think the best way to solve it is just plug it in. I guess we can plug this into here, and then we get, let's see, P1 over 2 is P2 over 4. So P2 equals P2 over 4 plus P3 over 2, which basically becomes, I think, 3P2 equals 2P3. And if you plug this, actually, this becomes 2P3 equals 1 plus P2. And if you solve this system of equations, you should get P2 equals half. That's just substitution. And I think you get P1 equals 1/4. That's the answer. So
Wait, can you explain like the states part, not like the algebra, but like the states part again?
Yeah. So P1 is the probability that if currently, like right now, the frog is on the first rung of the ladder, then P1 is the probability that it gets to the top. And P2 is if right now the frog is on the second rung, what's the probability that it gets to the top? And P3 is the same. So if the frog is on P1, the probability is dependent on, let's say, whether he goes down or up, right? So P1 is the current probability. This is equal to half times 0. Half times 0 because 0 is the, what do you call it? There's a half chance that you go down. And if you go down, now the probability that you reach the top is 0 because you fell off. And there's also a half chance that you go up. And if you go up, then there's a P2 chance that you get to the top by definition. So P1 equals half times 0 plus half times P2. That's, just how it works. Because you consider the next case, then one thing after one move, the problem after one move, and you take all possible cases and the probabilities of them, and then you add them up.
Okay, that makes more sense.
Yeah. The algebra hopefully is not too bad. Usually you can just substitute stuff. It doesn't take that long to solve the system of equations. Although it takes longer than the states if you know how to set it up. So this, of course, requires practice, but I don't have that much. Actually, I don't think it's in the homework. We can go over some practice problems, though. Actually, let me go back. You realize that P2 is half, and a lot of times... So P2 is half. That's what we found at the top right. But if you look at this thing here, it's a 50-50 chance to go down or up. So if you're in the middle, it's also a 50-50 chance that you get to the bottom or the top. So by using symmetry like this, you can often just simplify the equation a lot. So if P2 is half and you know that, now you only have to have one equation. You only have to do this last equation here to the right, and then you just get P1 equals 1/4 without even having to think about P3. Yeah, so it can be a lot. You can often simplify your work if you do symmetry, and one of the examples on the next page will do that. So make sure to use symmetry. All right. Does anyone have an idea of what the states should be for number one? I'll give you some time to think about it, but could you just have two rungs? Yeah. Not sure what you mean by that. If you have two rungs, it probably is half because the first roll determines. I mean, if you go up, you win. Oh, do you mean? Oh, you mean on this question? That makes sense. Yeah, two states, I guess. Um, so let's say the most recent one is tails. That doesn't really give much information about the previous flips, right? Um, because we need all four of these to match, and if we know the last one's tails, and then we flip heads, maybe we finished already, or maybe we just got nowhere, right? So you need more than two rungs, unfortunately, but not that many. Okay, so we want to have the least number of states possible, but we want every single situation to happen. So let's have a state for nothing, which is where we start off. Let's say it's p. That's actually expected value, so this is good. Expected 1. And now if it ends with heads, let it be expected 2. And another case we have to think about is heads, tails. Because now we're like partially like doing the actual sequence. If the first roll is a tails, or the first flip is a tails, then that doesn't do anything. That's just like doing nothing. But if it's a heads then a tails, now you're getting somewhere. You're actually starting to do the sequence. So let's let that be E3, and then HTT is E4. So okay, let's see. E1. Let's start from E1, and if you roll heads, it's E2, so it's half times E2. And if you roll tails, then it's just the same thing again. So rolling tails doesn't do anything. Is this equation correct? Kind of a loaded question there. So the previous question was probability, but this question is expected value. So it's a number of coin flips. So if you flip once, you have to increase the expected value by 1. So this is an important thing you have to remember every time you're doing expected value with states, because you have to increase the number of flips by 1. And let me do the others similarly. If you're at E2, there's a half chance that you just go back to E2 because you roll another heads, and there's a half chance that you actually advance to E3 plus 1. All right, and finally, if you have E3, oh, this is your mean equal sign. If you're at E3, there's a half chance that you roll a heads, in which case you go back down to E2. And there's a half chance that you go up to E4, which is 0. Because if you're at the top, if you already did the sequence, the expected value of rolls is 0, because you're already done. And then plus 1. That's a big one. Okay. So do these equations make sense? Little, yeah. So yeah, if the expected value, I mean, you're setting states for like, wait, okay, what part do you think is the most confusing? I'm not exactly sure. Yeah, it of course like it's a topic that requires practice and like a lot of things. So I mean, I can't really do it a lot of justice in like an hour 30 class. Um, I think like a lot of math things, you often like forget them just like a month after you see it or a week. So it may be good to just like instead of going in depth once because then you might forget it, just like go over it a lot of times. So I guess this could be like a first introduction to states, and then maybe later when you're doing counting again in some other class, you could go over it in detail and so on. An example of things that you forget a lot are like trig identities, because for me, I didn't remember them until like I took multiple classes on pre-calculus, and then like I finally understood it and remembered it. Hey, someone's here. Hello, Michael. Class is almost over. Uh, sorry, the it didn't appear on the Google Calendar for some reason because it was not in Summer Academy or something. It was in like MATHCOUNTS class instead of Summer Academy, so it didn't show up in the thing. Yeah, so I sent an email. Yeah. This lecture is being recorded though, so hopefully, you can, it's okay. Yeah. So we're doing states right now, and states is where you set a variable for each possible state, or for the expected value or the probability. So, yeah. Um, I guess we can just do number 3 now. Any ideas on what the states should be? This should be at random. One one 4 1 1 4 4 4. Um, well, those are the cases in which you can finish, but we do have to have cases for like everything. Oh wait, I think I know what you mean. So how many total cases? How many? Yeah. So remember what I said about symmetry, right? So if you're on 1 1, that's basically the same as if you're on 1 4, because you can just like it doesn't matter. You're like next to the vertex. So one of the cases can be you're on one of these squares, and another case can be when you're on one of the side squares because they're all the same. All these green circles are the same basically. And a third case is when you're in the middle somewhere. So even though there are 16 points here, we only need 3 states. And yeah, I don't know. Should I go over all the equations because they might not? They might take a bit of time and might be boring, but I'll just do it. So I guess we won't write variables. The red thing, the red probability, equals. Let's see. If you're on a red thing, there's a 3/8 chance. Hold on. There's a 3/8 chance that you go to another red vertex. There is a 4/8 chance that you go to a green vertex, and 1/8 chance that you go to a blue vertex. And since these are probabilities, we don't have to add 1 because it's not expected value. Yeah, hopefully, doing more examples will always make it make more sense. I don't know actually if I have a lot of homework questions about this, but yeah. And the other cases are similar. So if you're on a green square, there's a 1/4 chance to go to a red one, 1/4 chance to go to a green one, 1/8 chance to go to a blue one, and then 3/8 chance to just fail because you hit the edge. And if you're on a blue vertex, it's 1/4 to go in a green, 1/8 to go to red, 1/2 to fail, and 1/8 to succeed. So if the 1/8 to succeed would be 1/8 times 1. If you're here. Does anyone want me to go through the computations and stuff or anything? Or explain anything about states? Alright. Alright. That's good, that's good. Yeah. So, I just compiled a bunch of random problems and made up a few in the next 7 slides. So I guess these are homework kind of, although there are a lot of questions. And do you want to go over any of these, or should we just end the class? Any ideas? IDC? Alright. No one. Can we end it? Alright. That's fine. Okay. So thanks for coming, guys. Thanks for sticking around until 6:30. If you didn't arrive at 5, I apologize for any errors of the class stuff. Anyway, okay, bye guys. Alright.